You ever wonder how electricity really works? We flick a switch and boom, the lights are on. But what is actually going on inside those wires? Well, today, we're going to take a journey. We're going to follow the flow of electricity from a super simple circuit all the way to some surprising chemical magic it can pull off. Turns out, it's a force that can do a whole lot more than just power a light bulb. So here's the game plan. We'll start with a basic recipe for electricity. Then we'll figure out what makes some materials a highway for it and others a total dead end. After that, we're going to ask a kind of weird question. Can electricity swim? And that's going to lead us to its hidden chemical powers. And finally, to the super cool art of electroplating. All right, let's dive right in with the fundamentals. Think of it like baking a cake. You need a few key ingredients to get any kind of electrical result. So what's in the recipe? Turns out, you always need these three things. First, you need an energy source, like a battery, to give it that initial push. Second, you need a path for that energy to travel, like some wires. And third, you need something to show us it's working. We call that an indicator, like this light bulb right here. If you're missing even one of these, the whole thing just doesn't work. But here's the catch. There's one more crucial rule. The path has to be a complete, unbroken loop. It's kind of like a racetrack. If there's a gap anywhere, like a broken bridge, everything just grinds to a halt. The energy has to be able to flow from the source, through the light bulb, and all the way back home. Okay, so we know we need a complete path. But what should that path be made of? This is where it gets interesting, because not all materials are created equal. Some act like superhighways for electricity, while others are absolute dead ends. To really get this, we need to meet the charge carriers. And honestly, the best way to think of them is as tiny little delivery boys. Their entire job is to grab a package of energy from the battery and hustle it all the way over to the light bulb. If a material doesn't have any delivery boys, well, that energy has no way to get where it's going. And that's really the only difference between conductors and insulators. It's that simple. Conductors, like most metals, are just materials that are packed with these delivery boys. In the real world, we call them free electrons, and they're all just ready to go. Insulators are the exact opposite. They have no delivery boys on call. They just block the energy because there's nobody there to carry the package. So let's put this to the test. Imagine we slot a metal plate into our circuit. It's like opening the doors to a warehouse that's just full of delivery boys. They flood across, carrying the energy with them. The bridge is fixed, the circuit is complete, and just like that, the light bulb springs to life. But now what happens if we swap that metal plate for, say, a wooden block? Well, wood is an insulator. It has zero delivery boys. So the energy carriers run right up to that block and just stop, dead in their tracks. It's another broken bridge. The circuit's incomplete and the bulb stays dark. Simple as that. Okay, so we've pretty much got the basics down for solids, but this leads to a really cool question. We know electricity zips through metal wires, but can it travel through liquids? Can electricity actually swim? Right, picture our circuit again. You've got the wires coming from the battery, but instead of touching each other, we dip both ends into a glass of water. Is the bridge broken now? Or can that energy somehow make the jump across the liquid gap? The answer is, it depends on the liquid. See, pure water on its own has very few delivery boys. But if you dissolve something like salt or acid in it, something wild happens. The molecules literally break apart into these charged particles called ions. And these ions, they become the special ops delivery boys for the liquid world. Let's look at two quick examples. If you stir sugar into water, the sugar molecules just kind of float around whole. No new ions, no delivery boys, so no electricity flows. But when you dissolve salt, it shatters into charged sodium and chloride ions. All of a sudden, that water is just teeming with delivery boys, and it can carry a current. Pretty cool, right? But there's something else going on here, something even crazier. When electricity flows through these special liquids, it doesn't just pass through quietly. It actively starts changing the liquid itself. It kicks off some pretty powerful chemical reactions. Now, this is a huge shift in our story. The flow of energy is no longer just a passive trip from point A to point B. The movement of those ions, our liquid delivery boys, starts to break molecules apart and form totally new substances. Basically, electricity puts on a lab coat and becomes a chemist. So how do we know this chemical reaction is happening? What are the clues? Well, you might see bubbles of gas forming on the metal rods that are dipped in the liquid. Or you might see a thin film of metal starting to appear on one of them. Sometimes, the entire liquid can change color right before your eyes. And check out this amazing, real-world example. If you stick 2 wires from a battery into a potato, which, believe it or not, is conductive, and you just leave it for a while, something incredible happens. The area around the positive wire turns this greenish-blue color. Why? Because the electric current is causing a chemical reaction right there inside the potato. It's visible proof of electricity's hidden chemical power. Now, this ability to cause chemical change isn't just some neat party trick. No, it's the foundation of some seriously powerful technology. We can harness this effect to do something incredibly useful. Give everyday objects a beautiful, protective, and super shiny new coat. This is the art of electroplating. Probably the best way to think about electroplating is as a clever mask. It's this process that lets you take a less expensive object and cover it with a beautiful, strong mask made of a more precious metal. It looks exactly like the real thing, but it's an illusion powered by electricity. So what's actually happening here? Well, electroplating uses an electric current to literally pull tiny particles off of a piece of a desired metal, like shiny chromium or valuable gold, and then it carefully paints them atom by atom onto the surface of another object. So, how do you actually apply this metal mask? Well, you start with a special conductive solution. Then you hook up the object you want to coat to the negative side of a battery and a piece of your mask metal, let's say gold, to the positive side. The second you turn on the power, the electricity gets to work, dissolving the mask and perfectly depositing it onto your object. And this process is everywhere. I mean it, that shiny, scratch-resistant chrome on car bumpers, that's electroplating. Affordable jewelry that looks just like solid gold, yep, electroplating. Even massive iron bridges are protected from rust by electroplating them with a layer of zinc, a process called galvanization. It's a cheap material wearing a powerful protective mask. So there you have it. We've gone from a simple light bulb all the way to a technology that can protect a massive bridge. This clever mask of metal is all around us, making things stronger, shinier, and way more affordable. Now that you know the secret, take a look around. Where else can you spot its clever disguise?